cheated, without even cheating, couldn't you have gotten to 7 just using what the description is of a derivative? What's a derivative? 3 things. Slope. Oh, what's the slope of any line? Dun, 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 dun. What? That only works for lines. All right, well, or numbers. What about y equals 5? What would its derivative be? 0. Because any constant function, the slope will always be 0. Maybe we can cheat a little bit even without using basic rules. Okay, number 38. Ugh, isn't 38 from this nasty section? Let's keep going. We'll come back to him. Same with 40. 46. We'll come back to 38 and 40. That's in the nasty section. Were you guys able to figure out that f of x is x cubed and c, or a, is -2? No? Oh, this was such a good question. This was such a good question. All right, which one was that? 48? 46. Oh, this one, like as far as how this section is applied in all of AP Calculus and AP tests, this one is one of the most useful of all of homework. Did you guys watch number 47 to help you on 46? I heard one yes. It was different. It was different. Because what form, guys, what forever card, I think Patricia was just saying it, what form of the derivative was this one? F prime of a from forever card number 7, the second one, the limit as x approaches a of f of x minus f of a all over x minus a. But what form of the derivative was this one? Actually, not forever card number 6. Close. It's close. Because on forever card number 6 and forever card number 7a, the first alternate form, don't both of them have h going to 0 or delta x going to 0? So Michael's right. This is from forever card 6, this part, but we got to keep looking. And my question to you, are there x's and delta x's? No. I mean, there are, but what's in the x spot? An a. Pause. Get out your notes. Look at forever card number 7. I'm so worried that we're all like just blinking. We should have been filling out our forever cards. Not that you have them memorized, but you should have been looking at your notes last night. You have to match these with an f prime. And the crazy thing is at the very, 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 very beginning, in the directions you were supposed to write down, didn't you guys see you were supposed to be looking at forever card number 7? Because forever card number 6 says f prime of who? X. But what does this one say? F prime of c. And what can you think of c as being? A constant, yeah. So from the very, very beginning, from writing your directions that you're supposed to be doing, you should have known forever card number 7. So look in your notes at forever card number 7. If you have your forever cards, I guess you could have gone there too. Forever card number 7, there are 2 alternate forms, true? Does it make sense how 47 is the second, x approaching a? And how 46 is the first, delta x approaching 0 or h approaching 0? Now look. If I was to label this puppy, if I was to label, oh, Mrs. Christensen was here. I could have had her change that setting. Struggle. Sorry. Just reminding myself. What's this supposed to be? Guys, read the forever card for me. F of a plus h. Wait, hold on. But this one, they forced our hands. We can't use h. What do we have to use? Delta x minus all over h or delta x. Who are we supposed to be finding? F and c. Or if we want to think about it, we can say f and a, right? Okay, so look over here. I'm not looking at that. I'm not looking at that. Where's my a? It's been plugged into something here, and it's been plugged into something here. Can anybody figure out what a is just looking at this? Right? Who's in this spot? So what's a right away? Oh, a is -2. Now I need to figure out what's f. Who's f? Well, sadly, he's the guy that -2 got plugged into to make 8, and he's the guy that -2 plus delta x got plugged into. What do you see on the outside? I see a cube, don't you? Can't we say this is box cubed, input cubed, and what went in the box? So what's going on outside of a plus delta x? F. What's going on outside a plus delta x? Cubed. So guess what f of x is? Then check it. Well, then that better be f of a. It is. Negative 2 cubed is negative 8, and minus a negative 8 is plus 8. Oh, dun 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 dun. F of x is x cubed, and a is negative 2. Why is this good? Why is this exercise good? Kiddos, how would you have had to solve this by hand? 0 over 0, keep going. Not even cubed root, just cubed. And unless you know Pascal's triangle, which might make this a little bit easier, you would have had to actually do this times itself, FOIL it, and then do polynomial multiplication and keep going. That would be nasty to do by hand. But if we do, which we are today, going to basic and shortcut rules, if we can figure out who is f and who is a, hey, f prime of a is easy. Use the power rule and say, dun, 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 plug in negative 2. After all the work that I would have done, what would be our final answer? 12. Done. Pause. In section 2.1, how did you have to solve limits? The by hand way. The long way. The 0 over 0 keep going way. But if in section 2.2 and beyond we start doing shortcuts, which you guys have already seen one in the summer packet, the power rule, bring down the 3, make it a 2 to get f prime of x. Leave the x there, so bring down the 3, make it a 2, 3x squared, 3. All I had to do was plug in a, and I have my final answer, and I didn't have to solve any of that. But I couldn't have gotten this answer if I didn't know how to read the alternate form of the definition of derivative. We'll keep working on this for sure, for sure. This is one of the main reasons I forced you to work with limits in this section so that you can look at this and say, it's a derivative! It's an alternate form. It's a derivative at an a. It's a derivative of who? Hopefully we get to where it's super easy to say, oh, of x cubed. When? When x is equal to negative 2. So that when we get really good at our shortcut rules, this is going to be an easy problem to solve. All right, do we have any more evens? 68. Did they force your hand as to which alternate form to use? Oh, 66, sorry. Sorry. I said the wrong number. The right one's up here. Did they force your hand as to which one to use? You were just able to do either one from Forever Card 7? So they did the f of x minus f of a all over x minus a. You might have done the other form. This one's probably the simplest, because if you had done it the other way, did anyone do it the other way? No? Okay. This would be the easiest one to simplify the complex fraction. Guys, think like the person who did this problem. What did they multiply top and bottom by? 4x. Good. You multiply by 4x. 3 and 4 makes 12. The x's cancel. Multiply by 4x. The 4's cancel. 3 and x. Multiply by 4x. There he is. Oh, factor out of 3. Cancel out the x minus 4's. Plug it in. Negative 3 over 16 is the final answer. Number 76. Thinking about differentiable. A function will not be differentiable at discontinuities, sharp points, or vertical tangent lines. What did this guy end up having? A discontinuity at x equals 3. So since f is not continuous, since f has a discontinuity at 3, there cannot be a derivative there. Everywhere but 3. It's differentiable. Number 78. Where is that one differentiable? Everywhere but its discontinuity. And what's its discontinuity? Or where is its discontinuity? 1. Everywhere but its discontinuity. Huh. Oh, okay, that's totally different homework. Okay. I have the book up. I'm ready to go. Do you guys have any questions on evens or odds? No. 63. Okay, yeah, that makes sense. Maybe we'll grab 63. Oh, he was a video too. It's okay. Just something to be aware of. What's the other one I heard? 69? 29? So I have 21. You said it was 29 or 30, 39? 29. And then someone else said 39, right?
Yeah. 39, 40.
Oh, 39 is going to that section. Okay. So we have 21, 29. Let's go to, I already have a picture of this one started. Using the alternate form of the derivative. To be honest, well, real quick, Janelle, did you do the x plus h one or did you do the f of x minus f of a one? Oh, praise the Lord. If it was x plus h cubed, that would be really gross. Does that make sense? Okay, so then that's our a, just in case any of you guys are confused. They can use c, they can use k, they can use a, they can use b. It just means a constant. So x is approaching a of f of x minus, don't forget your parenthesis. So easy to mess up a seal. F of a would be plugging in -2, which would be -8. Let's do it this way. X minus a should be, like, if you plug in correctly, this is a way you guys can always check. If you plug in correctly in the -2, you should get 0 over 0, keep going. And if you ever didn't get 0 over 0, keep going with a definition of derivative. Can I say that? Yeah, you will have plugged it in wrong. That's something to keep in mind. But we have x cubed plus 2x squared plus 1 minus 4. 4 and 2 is 8, so we have -8 plus 8 plus 1. Those cancel. I just get 1. Perfect. Why perfect? Because what can I factor out? As soon as you factor out an x squared, actually, right? See it? Now I'm good to finish my limit. Did you find it? -2 squared. Oh, I don't even need that anymore. -2 squared is 4. Okay, number 21. Then 29, then we'll talk about that nasty section of homework. So number 21, what are the directions on that guy? Okay, when they say find the derivative, guys, what forever card are we using if we're using the limit process, aka a definition? Yeah, forever card number 6, because they didn't say which derivative. They didn't say at x equals a. They just said find the derivative. So who was able to get this one all the way and can walk me through the steps? AJ, go for it. Okay, so start it off for me. So f prime of x is equal for that one. Good. Go ahead and tell me what happened when you plugged in.
I have 1 over x plus h minus 1 minus 1 over x minus 1.
Thanks. All over. Pause. So what she's doing is f of x plus h. Remember, plugging in x plus h to the input spot, which is why it goes right there. F of x plus h minus f of x, steal it, all over h. How'd you keep going? Because this is a difference quotient, 0 over 0. Let's go. Multiply. So both. Okay. So x plus h minus 1, x minus 1, x plus h minus 1, x minus 1. What happened when you were simplifying? What was the next step? What did you need? I like how you're going ahead and doing that, but can you go ahead and just so everyone sees why you're changing all the signs, what should be included if you're just subtracting that answer? Parentheses is what I was thinking. But in your head, I think you were distributing, which is good. Just for other people that didn't realize what you were doing. So then you do distribute. And that's why you said, what did you say, minus x minus h?
Yeah.
Good. What ended up happening? Good. X's cancel. 1's cancel. Negative h over h. So what's, she might have said it and I just didn't remember. Because, yeah, that'd be weird, right? -1. So what else was supposed to be with the h all along? All along, but after the first step. So now I have, what happens to those h's once everything else is gone? Careful, don't say cancel, it goes to 0. Say the word reduce. When you reduce, it goes to 1. But that's a negative sign, right? So then how'd you finish this puppy off, AJ?
I still kept it like x plus h.
Okay, so you would have -1 over x plus h minus 1 times x minus 1, but that's in a limit, so how do you finish? Plug in. Since the h is still there, we don't need to plug in. H is equal to 0. When h is 0, don't we have x minus 1, x minus 1? Which ends up x minus 1 squared. Some of us don't like complex fractions, but they're not new. That's not to say, like, be ashamed that you don't get it. It just means if you're stuck on them, you might want to come in and work through with me a few examples. Number 29 is right underneath the video. So if you didn't understand the directions, it might have been good to go check out 27. For those of you that aren't accessing videos, I would start if I were you. And some of you guys are accessing and you're like, well, this was a different problem. I get that. So let's see where this one got tricky. You guys have the directions to keep me honest, right? So the first thing I see is find the slope of the tangent line. What did you guys choose to do? Forever card 6 or 7? Did you go f prime of x and then plug in, or did you do f prime of a? F prime of a is the first thing I heard. So f prime of, I'm going to say 1 because when you're given a point, the x value is the a. And they just gave me a y also. Oh, sweet, that's nice. They gave me an x1 and a y1. Anyway, Patricia, I heard you say f prime of a first. Did you use the first alternate form or the second? Okay. So let me plug into that really quickly. So she had the one where x approaches a of f of x minus f of a all over x minus a. Are we okay? Maybe you did the other form, and if so, it's going to look differently, but I'm doing one variation. F of x, I steal them. F of a, I take f of x and I plug in the a, which is 1. Was it 0 over 0? Keep going? So how do you keep going if you have square root of x minus 1 all over x minus 1? It's like I should be able to cancel, but I can't, or else I'm killing kittens because they aren't the exact same. So what do I need to do? Multiply by the conjugate, because what do I have? A square root. Oh, it's not giving me room, is it? So Patricia, keep going. What's my conjugate that I should multiply top and bottom by? Good. When I multiply by conjugate, foiling is nice because it ends up just being the first times the last, outer and inner cancel. If you keep the bottom all nice and factored, it's ready to reduce. And so at the end, you end up with, plug it in, square root of 1 plus 1, which is 1. Is that the whole problem? Oh, this just isn't pretty. It's only one part of the problem. They said find the slope. So for letter A, f prime of 1 is equal to 1/2. Does it also say tangent line for letter A? Okay. So why am I just really quickly able to plug in? Where did I get my y1 and my x1? From my point. How did I get my 1/2? Slope of the tangent line is the derivative. Could we have gotten y by itself? I suppose. That'd be y equals, do you guys get it by itself? No? 1/2 x plus 1/2? Agree. What was letter B? Oh, graph it. The nice thing is with letter B, don't we know what this basic graph looks like? So you could have cheated and been like, psh, I'm right. And if you're, I'm right, you could have just gone to the point 1, 1 and been like, hey, guess what? I found the tangent line, even if you were wrong. Cheaters. Anyway, just kidding. That should be what ends up happening when you graph the line and the original function. It should skim at what point? At 1, 1. And was there a letter C? Oh, verify? On the graph? Oh. I guess to verify, you could have just actually found the 0.11 and been like, yay, it's at the right spot. Or you could have used our really spiffy dy dx, I guess, such that x is equal to 1, and you would have gotten the 0.12. I guess that could have also verified what we saw yesterday on our graphing calculator to make sure that we're right. Is that okay, Iris? Cool. All right, so we did 21. We did 29. We did whatever was at the end, the one that Janelle had a question on, and we're left with 37 to 40. All right. Guys, we're not going to spend a lot of time on this section for one very important reason. We're not masters of this yet. We shouldn't be. We don't have to be. We shouldn't be. We don't have to be. This is just an intro to a very deep, not deep, a very important topic for the year. Being able to go between a graph of an original and a graph of a derivative and figuring out how they relate. Okay? Is this just like Bell work the other day, where we had a graph? Kind of, except in Bell work, do you remember? Who was the graph of? Yeah, it was the prime. I think it was G technically, wasn't it? But if you look at Bell work, it was a graph of G prime. But if you turn to the back real quick, it's okay, Bell work. Go find the one with the graph. I think it was the most recent one that we did. We had a graph of G prime, and we were talking about how it related to G. So look at our answers. I think it was like C and D, is that right? We have a graph of G prime trying to figure out how it affected G. So when G prime was a positive number, and how did we know G prime was positive? Because the y value of it was above. When G prime was positive, what was G doing? How was he behaving? That's letter D, I think, right? When G prime was a positive number, say it louder, G was increasing. Look at letter C. When G prime was a negative number. When G prime was a negative number, what was G doing? Okay, and why am I bringing that up? Check out these graphs. Thinking about pre-cal last year, couldn't we say that F is decreasing and then increasing? And so it's weird because we're going the other direction. It's weird because we're going the other direction, but here's what I can say. If F is decreasing from negative infinity all the way up to 4, I can say that F prime is not positive. That wouldn't make sense. What are all the slopes, guys? How are they sloped? Is this a downhill or an uphill? Yeah, so F prime is going to be negative. Wherever F is increasing, which would be on 4 to infinity, guess what F prime is going to be? Positive. And then what do you guys know about the slope of the tangent line at 4? If you're doing little baby tangents, skimming the graph, what kind of tangent line will be at 4 before you start going uphill? It's a horizontal tangent line, and what kind of slope does a horizontal tangent line have? 0. So I know F prime of 4 is equal to 0, which is why I didn't include him in either of the intervals. So somehow F prime, the graph of F prime, is going to have a point at 4, 0. It's going to be negative before and positive after. F prime. F prime is going to be negative, having negative y values before 4. It's going to be positive, having positive y values after 4. And once we cover section 2.2 and the basic rules, maybe you'll know why a quadratic function would have a linear derivative. A quadratic function. Maybe that's what this is. It's a parabola shifted right 4. That would be minus 8x. What happens when we take a derivative, guys? The 2 comes down, and what's the new power of the derivative? Every quadratic is going to have a linear derivative. Now, that's not quite as nice. Well, actually, number 38 is maybe even nicer. Didn't we talk about absolute value yesterday or the day before? What's the slope of an absolute value function everywhere on the left of this sharp point? It's a line. It's constant. Good. So do rise over run. Down 4 and right 4. Oh, down 4, right 4. This line, this entire part of the line has a slope of -1, right? How about this part of the line? Up 4, over 4. +1. What are the slopes of the tangent line or the slopes of the graph? The derivative. So guess what? F prime equals -1 for everything but 4. And F prime on this side equals +1 for everything but 4. Why? F prime is the slope. So y equals -1. It's a horizontal line. Y equals 1. It's a horizontal line. Why is there nothing at 4? What happens at a sharp point? The slopes do not agree from either side, so the derivative, which is a limit, will not exist. Was that yesterday, differentiability and continuity? This function's continuous, but the derivative of the sharp point doesn't exist. I leave it open. Oh, so that must be the graph of this one. Hold on. For this one, this is what's called a cusp. This one technically is called a corner, just in case you want to know names. That one's called a corner. That one's called whatever. Everything's fine. This one's called a cusp. Like the problem points, the sharp point. This one's called a cusp. That one's called a corner. What's different? Does the derivative exist? No. So it looks like this with a jumpy thing? No. That's not a line, and that's not a line. So it's not just one number for a slope. Our slopes are changing. Downhill or uphill? So where's my derivative going to be? Down. Just like this. Downhill, the derivative's down. Uphill, the derivative's up. Above or below the x-axis. So downhill, my derivative's going to be down. Uphill, my derivative's going to be up. But what's my derivative doing? If you're skiing, what's happening as you keep on going? This is getting steeper and steeper, right? So you're going faster and faster, right? Guess what's happening? It's going to -infinity. What? As you zoom in and zoom in and zoom in, this tangent line gets more and 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 more vertical. What kind of slope does a vertical line have? Undefined, because it's infinite. It's infinitely steep. It doesn't have a number attached to it. If there was a slope of 100, you could go up 100 and over 1. It has a number attached. A vertical line has no number attached. Up infinity and over not at all. So it's going down to -infinity. And then what's this guy going as we come in? Steeper, 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 steeper. Guess what he's doing? And how does the derivative not exist? The derivative doesn't exist. The vertical asymptote. The derivative has a vertical asymptote here where he had a hole here. Last but not least. What's the derivative right here at x equals 0? Skim. What kind of line is that? Horizontal. And every horizontal line has what kind of slope? Say it louder. David's saying 0. He's right. So guess what? The derivative has a point at 0, 0. F prime of 0 equals 0 because there's a horizontal tangent line there. Uphill or downhill before? Uphill. Oh, so somehow it's going to be above and then downhill, so the below. And this one's getting steeper, 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 steeper. And this one's getting steeper, 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 but in a negative way. Something like that. After these 4 problems, have you mastered the idea of how to think about a derivative graph from an original graph? Not even close. Why not? We just introduced it. And guess what? All this stuff in section 2.2, basic derivative rules and the non-basic ones, the rules are going to help you start attaching original functions with their derivative functions. Will also help with the graphing thing. So we just got the bare minimum idea of how to think about a derivative graph with an original graph. You're going to see it in homework every now and then. When you do, do the best you can. Bring your questions to class, but you're not supposed to have it mastered yet, so it's okay if it's confusing. The more rules we learn, the easier attaching original graphs with derivatives or derivative graphs with original will become, so do not worry. Section 2.2a, basic differentiation. I have split section 2.2 into 2 parts. because I want to talk about just the rules, then I want to talk about the motion applications, the physics-y stuff. Ooh. Ready for that, Nick? Don't worry. It's much different than the physics stuff you faced last year. What's going on in calculus? Well, you got this practical tool called a derivative. What's he for? Well, he's used to calculate and study rates at which one quantity changes relative to another. And we've talked about descriptions. Oh, he's the slope of the tangent line, slope of the graph at a point, instantaneous rate of change. But how is he used? To calculate and study rates at which one quantity changes relative to the other. History. Newton versus Leibniz. We don't have time today, but we might watch it tomorrow. A quick, silly, but informative video that talks about the huge controversy of who discovered calculus back in the day. What? The vector video. You just want to watch Despicable Me. It's so fluffy. Last year's rummage sale for missions, it was great. There was a huge stuffed unicorn that someone won. Where would that have been from? Universal? Yeah. I took a fun picture. It was exciting. What? Probably not. I feel like they don't give those ones away at Universal. Even if you make so many baskets in the hoop. Is it really though? Do you remember the movie? I'm not sure that he was enjoying his piranha gun the whole time. I have a preserved piranha from Brazil. That's fun. Then it goes floppity flop flop and bites his nose. Poor piranha. Animal cruelty. Surprised that they didn't go advertising against that one. The question is, did anybody actually try to make a piranha gun? That's the real question. I feel like somebody, right? I think so.
I want his keyboard. When they were trying to break into his house, they were just like slapping the keyboard and stuff.
He had the moat and he had all the things in the moat. You guys ready? Is anyone still writing? Uh-uh. All right, cool kids, it's time. The crazy thing is you already saw this in your summer review packet. We just haven't been able to make it a forever card yet. If you truly did power through 2-1, do the homework to 2-1, you have now earned the right to start using the shortcut rules. Shortcut rules like, don't worry, I got it. The derivative. Hey, do we know the terminology now? ddx means derivative of? Ooh. Derivative of what? A constant. It's going to be a y equals a constant is always a flat line. A flat line always has a slope of 0. So derivative of any constant, 0. Power rule. That's one we've talked about multiple times, and some of you mastered it in the summer review, and some of you were like, yeah, I just kind of limped along. Now it's time for us to get good at it. Bring down the n and subtract 1 from the power. Constant multiple rule. What if we don't just have an x to a power? What if we have a constant in front as well? If we have some sort of constant times a function, we're trying to find a derivative. I'm going to go ahead and write that underneath because I'm starting to run out of room. Like with limits, the constant, like with limits. Careful, I can't use that for every derivative rule, but this one I can. Like with limits, the constant can be considered separately. So c times f prime. And a quick application of that using the power rule from up above means if I was trying to find the derivative of c times x to the n, it would end up being n times c x to the n minus 1. One quick application, if I have some number multiplied by x to a power, I bring down the power, it gets multiplied by the constant, and I decrease the power by 1. That's just one application. Huh? It's an example of constant multiple. It's an example of constant multiple. Sum and difference. If I'm trying to take the derivative, I'm some sort of addition or subtraction. We could say f of x plus g of x. I can just take the derivative of f plus the derivative of g, whatever those derivatives can be. Sum and difference rule. Wait, sum and difference. Guess what happens if there's a minus instead? Not much changes. So if it's f plus g, it'll be f prime plus g prime. If it's f minus, it's going to be f prime minus g prime. Sine and cosine. Sine and cosine. The derivative of sine of x. Why this is true is not basic, but the fact that you need to have it so memorized that it's just like off the tip of your tongue at any point whenever you see sines and cosines is why I'm putting it under basic. The derivative of sine is cosine, and the derivative of cosine is sine. Except it's not just positive sine, it's negative sine. I did not make that emphasized enough. The derivative of cosine is negative sine of x. And exponential functions, without going too deep, the derivative of e to the x is itself, and someday we'll see why. The derivative of e to the x is itself, and someday we'll see why. These are the basic rules. There are much more involved trig rules, much more involved exponential and logarithmic rules, much more involved product, quotient, chain rules. But these are the basics. These are where we're going to begin. And this is forever card number 9? Basic derivative rules is the title. The content, everything inside. Forever number 9. So with that, if I was to take these examples that I wanted us to solve, just to give us a taste of this, and if I wanted us to find dy dx for these functions, can you guys read the functions? I know they're kind of small. We have y is equal to negative 3x to the 12th, and we have y is equal to 1/2 x to the 4th plus 7. What rules go into us solving letter A for dy dx? Power rule and technically constant multiple rule. By putting the two together, we realize we can just bring down the 12 to multiply it by the negative 3, and x is now to the, so we end up with negative 36 minus 11. Whoa. Minus what? It is 11, I know. Struggle when you have to slow yourself down. 12 minus 1 is 11. What's my derivative? Negative 36. X to the 11. Is everything that easy? No, but that's the beginning. We could keep deriving, but then that would be something different called the second derivative and the third derivative and the fourth derivative, different meanings than the first. The second derivative is going to be something, if this was motion, this could be position, this could be velocity, the next derivative acceleration, the next derivative jerk, the next derivative, I don't know. If you're jerking in a car, there's an actual mathematical measurement for that. Anyway, yeah. How do we take the derivative of this guy? Constant multiple. Yeah, we could do that. So we could say that this is equal to 1/2 times. How would we take the derivative of the inside? Isn't this a sum and difference rule? Sum and difference says to take it one piece at a time. So take it one piece at a time. What's the derivative of x to the 4th? Bring down the power rule. Make it x to the cubed, because 4 minus 1, plus, what's the derivative of 7? Y equals 7 is a flat line. Always, always, always 0. Or think of it as, you can if you want to, 1/2 x to the 4th plus 7x to the 0. Bring down the 0. That poof is gone. What's my final answer? 2x cubed. Does it get more fun than this? Oh, just you wait. Tomorrow we're going to have a competition. Maybe you guys should practice tonight just a little bit. Sometimes it can be really, really helpful to rewrite the function before deriving it, but we'll see that tomorrow. Let's go ahead and take one last example. Oh, I'm not going to have time, am I? Okay. How would you guys at least think about taking the derivative of, pause, something like, go ahead and pack up, that's okay, 5x times the square root of x. Bring down what? We could make this 5 times x to the 1 times x to the 1/2, which would be 5x to the 3/2. And that's just why. We're going to learn tomorrow. Sometimes you got to rewrite before you derive. Bye, cool kids. I'm taking the derivative. You guys can get out of here. Bye.
For some reason, I didn't fall asleep in Patricia's seat, so I'm definitely going to take it.
All right. Sounds good to me.
Today was actually.
I know. You were like totally tuned in.
I know. I was like, what the heck?
Hey.
I'm in Patricia's seat.
And she doesn't mind her seat being up front, it seems. So we'll take it.